Okay, so this is the second part of two videos where I'm trying to set out some kind of strategy for setting out a quiz type question or exam type question with regard to VIX. We've just estimated in the previous video this value here, which is based on a variance estimate, and we've run this for the option chain data for the near-term maturity. In addition to that, you've got to do exactly the same, perform the same exercise. In terms of estimating this, we have to go below and re-estimate another variance, but for the longer dated, far term option chain data, and we're using the same identity again. Important to note here in this estimation that for the variance, we need an F and K0. We've already identified K0's obtained as being the exercise. K0 is the exercise that is consistent with the call and put, where the difference is minimized between those values. Now F, however, if we go back to our exam or quiz style question, the F here index is that K0 again, so it's the strike associated, it's the K0 plus E or T times the call minus the put, where the call minus the put are associated with the minimum difference. So for instance, taking that formula again, taking this formula, how do we implement this? Where is it being used in terms of our estimation? Well, we used it here just in terms of our estimation here for the variance. We did have an F estimate, and F I took from here. Now, how is that F being produced? There's two F's in fact. How's that F being produced? Well, F is the strike price, K0, so the 900, and in each instance here 900 at both these exercises correspond with the minimum difference between the respective call and puts. Okay, so F, the F is equal to K0 plus ERT. For the shorter term, or is this maturity, it's the 15 days divided by 365. And for the longer term maturity, for the F0, the longer term maturity was the 44 or 43 days divided by 365. In estimating F, so K0 is the strike price. Okay, so K0 is the strike price, 900, where we have the minimum difference between the call and the put, and then we multiply by ERT, where E is the exponential term, R is the risk-free rate, T corresponding to, in this instance, the lower maturity. Okay, that produces our F, and the strike price is the 900. It's the strike price immediately below that F, and sigma we worked out in the previous video, but F and K are being used here. Now that estimate is done again. We have to estimate F2 if you like, or the second F, in terms of this estimate being performed the second time. We have to use the second set of chain data to get this sigma squared subscript 2, and again we go through the same process, identify the exercise with the smallest difference between the corresponding call and put. Okay, we multiply by ERT, E exponential term, or the risk-free rate of 1.16%, and T would be for the longer time period. Okay, so we can observe that. And then again, it's the call and put identifiable associated with these values here. Okay, so it's the 31, 40 and 30, 20 are the respective call and put values. Okay, and that allows us to produce then the strike price, sorry, the forward rate, which we then use to estimate the variance subscript 2. Okay, that second value. And then the final estimate, if we go back to our exam style question, we've got to unify then all the different threads. So if they take that sigma squared subscript 1, sigma squared subscript 2, and we have to express in terms of a weighting in terms of time. So let's just break that down into its actual components here for a moment. We could say T1 sigma squared 1, I identify that as being this green component, and then this bit here as being the blue component. And we can make the estimate here in green if we just say, okay, equal to, what's T1? T1 is equal to 15 divided by 365, because there's 365 days in a year. Open multiply, open bracket, sigma squared subscript 1 is this value here, and then we multiply that in turn by what? Well, these are day values, and end subscript T2, it's just number of days, if you like, so we can put that in as being 43 days minus 30 days, end subscript 30 days, and divide that then in turn by NT2. Again, it's 43 days, 43 minus NT1, 15 days. Okay, and we get a value of 0.01249, which corresponds to the value that we have here. So basically, to express these as values, 15, Y15, 15 over 365, that's the maturity to the near-term contract. F13 is the sigma squared 1, this value we've worked out already, obtained from this. The 43 days, it's the amount of days remaining until settlement. We had written in the question originally, we had said 44 days. 44 days to the short-term contract, if we can find that, and 16 days for the short-term contract. So 44 days for the long-term contract and 16 days to the near-term contract. But we take a day off, we remove a day. So it goes down to 43 minus 30 divided by 43 minus 15. Again, in a similar fashion, we can do the same. Below here to get this element in blue of the calculation. So we're headed for this VIX. We go back to the exam style question. That's what we need to calculate, but we need to estimate now with the sigma squared 2, this second element of the VIX estimation. So in order to perform that, again, this instance, it will be 43 days divided by 365 days in a year, multiplied by the variance for the longer or the further term contracts, multiplied in turn by, again, we follow the logic here, 30 days minus NT1 would be 15 days divided by open bracket 43 days, 43 minus the shorter term contract, 15 days. Okay, and we get 0.00368182, which is the same as this value here. And then the last part of this is to take both of those values. Okay, so in terms of running the VIX estimation, then we take both of those estimates and we say, okay, it's I'm going to create a bracket and then a second bracket, and we need to basically, so we take this term, that value, and we add the second term here, which is what we've just done here. So I'll just add this value here. Let's do it this way, plus this value here. Okay, and that's going to get multiplied in turn by 365 days, 365 divided by 30. Close brackets. And because it's a square root, because this is a square root term, okay, the square root here we'll put to the power of 0.5. And we get 2433. Okay, 2433, 66, 66, 869, 869. So the terms are the same. So this is the VIX value, and it's generated by using this expression here. Okay, so this expression here is driving, going back to the question in the exam or a quiz style question for VIX, we're trying to calculate the value of the VIX index. It's two maturity dates. We have the 16 days, we have the 44 days. Note that the 16 will become 15 days in terms of remaining maturity. I explained that in the previous video. This is 43 days. We've got to work out the variances. We've got to work out the forward prices, the K0, and then the VIX level. In order to estimate this, we need F. In this video, I explained how to get F, how to identify K0, this value here in terms of our K0, ERT for the short-term maturity, and then how to get the call and corresponding put price appropriate for estimating F. And then once we obtained sigma squared for the shorter term contracts, we must obtain sigma squared for the longer term contracts, and then we've got to take both of those and integrate into this overall VIX estimation, and that involves us weighting the sigmas by the relative weight in terms of days to maturity, and we're trying to work out the VIX in theory for a 30-day window and then annualize that figure. So the N365 divided by N30 is, if you like, an effort to annualize our VIX figure going from the 30-day window to an annual window. Okay, so going back to our Excel, we estimate sigma squared subscript 1, sigma squared subscript 2. We apply the weightings that are appropriate for the VIX formula. Then we combine them and take the square root, and we extrapolate to the going from the 30-day window to the 365 or the annual estimation, and that allows us to produce a result in terms of, if we want to express as a percentage, we could multiply by 100. Multiply by 100, which is what we have here. And of course, we get to 24.3366. And you can see the two values are the same.